don't know about you, but I kind of hate to memorize things. I have to sometimes, it's just required, but I try to avoid it and try to find ways to get around it or to derive things or remember things without memorization if I can. So in my chemistry classes, we get to the gas laws unit of instruction, and there are a lot of gas laws. One way to sort of get around having to memorize all the gas laws is to be able to derive them from a single equation, the ideal gas law. And students always have a reference sheet, in my classes at least, always have a reference sheet for the ideal gas law. So they can just look up the ideal gas law and, if necessary, derive any of the other equations. And this video is going to be one in which I show you how to get that done. So when it comes to gas laws, there really is only one gas law that you need to know, and that's the ideal gas law. And if you are in an honors class, that's a prerequisite for AP Chemistry. This is going to be your set of test references. It's the AP test references, and that's the ideal gas law listed in your references. If you are not, at least in my honors chemistry classes, the ideal gas law is also listed in your test references. Let's see here. There's the ideal gas law, and if you're able to use this set of test references because you're in a lower level class, or at least not the highest level class, you also have Charles' law here, and here's the combined gas law. Here is Boyle's law. That's Gay-Lussac's law. But when you get right down to it, except for knowing the names of Charles' law and Boyle's law and so forth, you can derive all the gas law equations we use in a high school chemistry class from this equation. So let me explain what this equation is all about. Each of these symbols means something different. These are dimensions of measurement. Now, a dimension of measurement is different from a measurement unit. A unit of measurement measures or tells you what kind of measurements are being done, but they don't tell you the dimension of measurement. For example, P, in the case of this gas law, this ideal gas law, stands for pressure. Well, I can measure pressure in many different units. I can measure pressure in atmospheres, in kilopascals, in torr, in millimeters of mercury, even in pounds per square inch, although in chemistry we just about don't use pounds per square inch because that's an English measurement. We just avoid those. Volume can be measured in different ways. That's what V stands for. N, the small letter N, is the symbol we use in chemistry for the number of moles. And moles are a counting number when you get right down to it. It's it's like a dozen. A dozen means 12. A mole of something is 6.022 times 10 to the 23rd of that thing. The nice thing about the mole is it allows you also to convert to other things, because you can convert directly to molar mass, or the mass of a chemical formula, a chemical substance. It's the molar mass is the sum of all the atomic masses. Atomic masses come from the periodic table. The sum of all the atomic masses of all the atoms in a formula, written in units of grams. R is the gas constant, or sometimes called the universal gas constant, or the ideal gas constant, or the perfect gas constant. And T is the temperature in the system of measurement we call Kelvin. That's the absolute temperature scale. Now, all of this, all the other gas laws we use, Charles' law, Boyle's law, Avogadro's law or Avogadro's hypothesis, and Gay-Lussac's law and the combined gas law can all be derived from this. And let me show you how. First of all, let's write down this gas law. PV equals nRT. Now, R is a constant, and that means that if I rearrange this equation in such a way to have R just on one side of the equality, the equal sign, all by itself, then no matter what PV and R and NT are, it's always going to equal R. And let me show you what that means. I'm going to rearrange this equation so R is by itself. So I've got PV over NT T equals R. So any value for P or V or N or T, when they are multiplied and divided as is shown here, it's going to equal R. Well, that means that any P, V, N, T will equal any other P, V, N, T. And we might write that with P sub 1, V sub 1, N sub 1, T sub 1 equals P sub 2, V sub 2, N sub 2, T sub 2. Okay? Now, if any one of these or two of these variables don't change, say pressure is the same on both sides, then I can divide both sides by pressure 2 or pressure 1, and it cancels out. Because if the number for pressure is exactly the same, and you divide that same number by the exact same number, well, they equal 1, and it basically is not even there, because anything multiplied or divided by 1 just gives you the same number. So let's take a look at this. Let's use this then to derive all of our other equations. Let's say that pressure is going to stay exactly the same. So I'm going to write that down with pressure being in red here, so we can kind of keep it separate here. Pressure is going to be the same for this equation. So I got pressure, volume, number of moles, temperature equals, here's our pressure that didn't change, volume 2, number of moles 2, temperature 2. If it stays the same, it cancels out. I can get rid of pressure by dividing both sides by 1 over pressure. And since pressure is the same number, then this number divided by the same number, or just like 4 divided by 4 gives you a fraction that equals 1, and 1 multiplied and divided by all this just gives you the same number. So they basically go away. So that's all going to cancel out, and we end up with V1 over N1 over T1 equals V2 over N2 over T2. Now there's not a name for this gas law. We just sort of I'm showing you how you can get there. But if it's exactly the same on both sides, you can more or less leave it out. Well, let's leave out number of moles here. Let's take that same equation and leave out number of moles. Let's say that moles don't change. Now, how would moles change? If you added more gas or took some of the gas away, or you ran a chemical reaction that produced more particles or molecules, that would increase or it could decrease the number of moles. Well, let's just say moles don't change. Then we have P1V1 over T1 equals P2V2 over T2, and that's called the combined gas law. All right, we've just derived this equation from that. All right, let me just remind you where we went from. This is the ideal gas law. We set it up here so it equals the constant. R is the gas constant. And if these variables, these things that can change, are always equal to R, then any one of, because R always equals R, then any set of these is going to equal any other set of those. So P1V1 over N1 T1 is equal to P2V2 over N2 T2. All right. Then if the P's are exactly the same, they cancel out, you get this. If the moles don't change, moles cancel out, you get this. That's called the combined gas law. Let's say that moles and temperature don't change. Well, then you get P1V1 times P2V2, and we call that Boyle's law. Now, in almost any chemistry class I know of, you have to know that this equation is Boyle's law. You have to know in almost any chemistry class I know of that this is the combined gas law. Those are one of 4 gas laws in almost any high school chemistry class you're going to have to memorize. You're going to have to know that that's what it is. That's the name of it. But they can all be derived. The equation itself can be derived from the ideal gas law. All right, let's say that the pressure and the number of moles don't change. Well, then you've got Charles' law. Okay, because pressure and volume didn't change, we're just left with V1 over T1 and V1 over T1 and V2 over T2. Okay, that's Charles' law. So these three equations and the ideal gas law in almost any chemistry class in high school, you're just going to have to be able to name them. Okay. Sometimes in some chemistry classes you have to name Gay-Lussac's law, but it may not be required in some classes. But Gay-Lussac's law you get from all of this if volume and the number of moles don't change, in which case you get P1 over T1 equals P2 over T2. So since the volume of the gas didn't change and the number of moles didn't change, you're just left with P1 over T1 and P2 over T2. Okay, so any of these, like I said, any of these gas laws can be derived from this one right here. And it's really easy to remember this one if you just sort of sound it out. PUV-NRT. PUV-NRT. So PV equals nRT is the ideal gas law. Just remember PUV-NRT, PV equals nRT, derive everything else. If you want to memorize all these equations, have at it. But if you like to sort of back yourself up by being able to derive things if you need it, or let's say, as in my class, you're not really required to name Gay-Lussac's law here. You could still know how to use it if you have a problem where only pressure and temperature change. When you're going through the word problem and only pressure and temperature change, you just cancel everything out from this. So if you can remember all that, it's really pretty simple math. You probably learned it, even though you may not remember the process. You were taught that process in any of your algebra classes. So that's how you can derive any gas law equation from the ideal gas law.